Welcome to Group 31's Thesis B presentation of our Unmanned Aerial Bushfire Assistance Vehicle. My name's George and I'll be taking you through the project overview as well as the system's integration. Australia's bushfire seasons have been increasing in severity and duration each successive year, posing an increasing social, economic and environmental threat. This was particularly evident in the recent 2019-20 bushfires, which saw 19 million hectares of land being burnt, contributing to the loss of 30 human lives and over 1 billion animals. It is this problem, alongside the identification of current limitations in Australia's prevention and mitigation strategy, that form the problem definition for this presentation. This thesis responds to the task of developing a system that is demonstrably effective in prevention mitigation against Australian bushfires through the use of a UAV-AB system. The design integration deals with the formation of a detailed system design that could be proved effective in addressing the evolving problem. Transforming the findings from Thesis A into a virtual system involved mapping the opportunity areas into functional requirements, which were expressed as design parameters to get an understanding of the layout of the system. To ensure the design met the requirements of the project brief, relevant outcomes, performance metrics, and constraints were constructed that reflect the original design brief. The opportunity that was recognized by our team was the development of a smart drone network that dealt with the detection, initial suppression, and autonomous situational analysis through the integration of a smart payload. This section dealt with encapsulating the process and roles that the drone system would adhere to, the conceptual design process of the attachment, the stability of the system to ensure it's reliable and feasible, and the framework of the prototyping of the system. These areas are formulated into Table 1 to show the outcomes that were expected of this section, with performance parameters also being used to measure the level of success of the system. The methodology chart in Figure 1 also summarizes the approach taken in this section. The drone network was defined in 3 segments: the mother drone, which is utilized for early detection and mapping through the form of a fixed-wing drone, the ground station, which is used to relay information to RFS and override drone control, and the secondary quadcopter drones, which are deployed to the site of ignition upon detection. The secondary drones have different variations defined through the attachment they will use, which allow them to assist in fire suppression, search and rescue, or general data assistance. The process in which each signal is sent upon the detection of fire was determined through statistical inference and assuming time intervals for the modules shown in Figure 2. The detection and mapping phase were then depicted using a MATLAB script, which allowed a better visualization of the integration between detection and deployment, which was initially found to be a downfall in Australia's current methods. The system was then applied to the area of New South Wales to check its feasibility, and through prioritising high-risk areas, the feasibility was confirmed to be reasonable and in association with the first outcome. The physical interaction of the system is shown in the schematic, with the quadcopters active at the first scene and fixed-wing mother drone overseeing the operation. The functional requirements of the attachment were then mapped to design parameters to produce 3 conceptual designs. After a concept selection process, the conceptual design 1 was determined to be the best, and as a result was improved in association with the project needs and constraints. The result was a hollow encased carbon fiber design which had 2 variations: an encased design for the purpose of carrying visual aid technology shown in Figure 5A, an encased design with the purpose of carrying and deploying fire suppression balls through a lever mechanism shown in Figure 5B. To increase the reliability of the camera system and accuracy of fire suppression deployment, the vibration due to external forces was required to be minimized. This was done through the introduction of an active isolation system with feedback shown in Figure 6. A linear system analysis proved that the introduction of this system increased with the stability and reduced long-term vibration, which would have impeded the quality of visual aids. This is shown in Figure 7, through the uses of a time response plot for the final system. The final design of the system integration was then measured against the performance metrics defined for this specific section. Each performance metric was justified, ensuring the design assisted with the growing problems of increasing bushfire activity and did not exacerbate it, as summarized below. The key features are the reduced reliance on volunteers and aircrew, which assisted in achieving social, economic, and safety goals, the reduction of current harmful mitigation strategies that use large amounts of harmful chemicals and emitted high amounts of CO2, assist the environment, and increase the economic impact through a simpler design. The final design is lightweight and also addresses the environment and economic effectiveness through its early arrival technology. This part sets out the structure for the system design solution, and as a result, the other sections will be utilized to further explore specific areas of the system feasibility. Some questions that may be asked about this section are shown here below. I will now hand over to Ivan to discuss the implementation of technology and software into the drone.
Thank you, George. Hi, my name is Ivan, and my section is Software and Technology, and I'll be going through different sections of my portfolio regarding the same. Bushfires are an annual occurrence in Australia and have caused a loss of $100 billion, along with the lives of many animals and the balance of ecosystems over the vast expanse of Australian forests and coastline. The uncontrolled fire couldn't be contained due to the use of outdated technology against it. The scope of this portfolio tries to find innovative ways to help mitigate the spread of bushfire, avoid the disaster caused by the last one. Software and technology in this portfolio highlights the upgrade that existing equipment could incorporate in order to have an advantage over in this situation. Thesis A discussed the requirement of different technology, whereas Thesis B covers future work on the preliminary design proposed in Thesis A. The methodology used follows the steps shown in Figure 1, started with reviewing Thesis A followed by research on preliminary design. The final concept post-research was refined by making adequate changes. Proof of the concept was found in existing experimental work of published authors. Finally, the final design selection was presented in terms of the report and a presentation. Digging deeper, technology is divided into detection, navigation, communication, sensors, and software. The existing tech in this field will be deployed in a multi-UAV system comprising of the mother drone, search rescue drone, ground assistance drone, fire suppression and brake drone, and ground control station. Multiple other options were compared using Pew Matrix, and the final design selection are displayed further ahead. The mother drone is equipped with the Epsilon 175 payload, which is a powerful camera enabled with a 360-degree rotation gimbal pre-installed. The search and the rescue drone is equipped with the CGO-ET low-light camera, which uses infrared technology. Ground assistance drone uses a thermal FLIR View Pro R. Fire suppression uses Zenmuse Z30 visual camera. Early detection software is set up at the ground station to analyze the collected footage. More on it ahead in the presentation. Final selection and navigation was the flight control unit or the autopilot and the modem from UAV navigations. All the UAVs are equipped with the same autopilot, whereas the modem is set up in the ground control station. Figure 3 shows a navigational circuit which includes GPS as well as IMU. Final selection and communication uses the same autopilot and the modem for transferring information to and fro from the UAVs. Additionally, an antenna is added to the ground control station to improve quality and the range of connectivity between the drone and the ground control station. Communication chapter also covers tracking and recovery of objects and lost UAV during the mission. Figure 7 displays the same. Figure 6 displays the final communication setup between the GCS ground control station and multiple UAV systems. Trisonic Mini is an additionally added sensor to the system. It can actively track wind direction and speed, simultaneously also record data like temperature, air pressure, air density, etc. This information is vital to understand the spread of the fire and will help firefighters predict the direction of the spread. Figure 10 displays the result obtained from the early detection software. The original image with the fire, when run through the course, detects fire and lets the people in the ground control station know about the same. This would help cut down the labor costs while running the mission. Answering all the FAQs in sequential order, the final design selection fulfilled all the performance metrics and constraints defined by the project brief. The functional requirements were also defined based on the same. The validation of technology and software used on the basis of experiments conducted by published authors, the existing work is used as a working reference to support the claims in this portfolio. The cameras and other equipment were compared to other equipment based on Pew Matrix. The devices with the highest points were deemed the most suitable for the mission portfolio. Handing it over to Cedric, who will go over his portfolio with detailed information about the UAV selection and power source selection. Thank you.
Hi, I'm Chaoming Guo. I'm going to introduce a portfolio of UAV selection and refinement. According to proposed system, four types of UAV with different responsibilities are deployed to mitigate bushfire, including one mother drone and three secondary drones. The preliminary objective of this section is to select the most suitable commercial drones from the existing market. Another major aim is providing solutions to limitations of selected drones. To be more specific, to design the most feasible power solution regarding to flight time extension. This flowchart illustrates the methodology of this portfolio. Firstly, previous research related to UAV design and firefighting applications was reviewed. Following the portfolio of design integration, camera selection, as well as fire suppression system design, payload constraints and performance requirements were defined. These factors further determined the selection of UAV. During design process, a problem of fire suppression UAV was occurred. Since a fire suppression drone has to carry an entire fire suppression system of 5 kilograms, the flight time is insufficient for mission completion. Therefore, four power solutions were generated from previous research. In design modification, given seven constraints including safety, cost-effectiveness, flexibility, reliability, durability, sufficient range, and severe weather operations, P matrix was applied to determine the best power solution. Applying performance matrix into UAV selection, three commercial drones were defined. Artisan as a vertical takeoff and landing fixed-wing UAV equipped with optional cameras was selected as a mother drone and mainly provides early detection in wide range. It's able to cover 450 kilometers and fly over 6 hours consistently. DJI Mavic was chosen to carry out missions related to search and ground assistance due to the supreme flight performance among light-duty quadcopters. It can keep operating for 30 minutes with 1 kilogram payload. DJI M600 as the most stable industry hexacopter was selected as a fire suppression and firebreak UAV since it has shown great performance on previous missions related to firefighting. However, the flight duration of this drone is only 15 minutes with 4 payload. Hence, power optimization is essential to be conducted. According to Pew Matrix, battery replacement obtained the highest score and was selected as a power solution. After comparison of required thrust and provided thrust, Tattoo 10,000 mAh was selected among the list of UAV batteries with different capabilities. These batteries can be easily installed since it's designed with compatible cables for UAV and has similar dimensions as original batteries of DJI M600. With calculations and assumptions, the optimized payload is 7 kilograms and the hover time can reach 46.8 minutes. There are two most frequently asked questions related to this portfolio. You may ask, why select UAVs from market rather than design a UAV? Since the development of drone market is rapid and advanced, the aesthetics and performance of commercial drone have been optimized at a high level. Many articles also evaluate the firefighting performance of existing drones and concluded with a satisfactory result. Therefore, it's better to conduct modifications on existing drones according to the specific constraints. In terms of the second question, what's the real hover time of the fire suppression drone since the hover time is based on calculation? With a limited time and budget, it's very difficult to build a ratio 1-to-1 prototype and conduct experiment. But this has been outlined in the future work. Even though future effort is needed, in my calculation, assumptions were made according to real-world conditions, so the discrepancy between theoretical and realistic results may not vary too much. Now let's move to material selection and design presented by Harrison Garlick.
Thanks, Chao-Ming. I'm Harrison Garlick, and I'll be outlining the material selection strategies and final design for the Unmanned Aerial Bushfire Assistance System. Following on from the conceptual design stages outlined by George, 4 major components emerged for material selection and final design proceedings. The components outlined in the next slide allow for the mounting, protection and support of a variety of cameras and technology to suit the UAVs selected by Qiaoming. After the overall dimensions were determined, material selection procedures began with the outlining of objectives and constraints based on loading conditions. Material screening and elimination using Ashby's charts produced candidate materials that were then ranked using a utility function and rate by average value to determine the optimum material choice. Once the material choice has been made, finite element analysis is used to verify the material selected and the overall geometry to ensure the system components do not fail under loading conditions. Once the material and geometry is verified, the assembly and the final design of components is completed to ensure complete system integration and provide a sufficient design for bushfire mitigation and prevention, and to have a positive impact on an environmental, social and ecological stage. The 4 major components are the DJI M600 mounting platform to mount the fire suppression and modular payloads, the DJI Mavic 2 mounting platform to mount the modular payload. Both of these mounting platforms require maximum lightweight stiffness for optimum performance and limited deflection whilst offering stability for quality camera operation and flight. The fire suppression payload carries the Elite A fire suppression balls, which will be used to suppress small spot fires and aid in bushfire mitigation. The payload is required to be lightweight and strong, and fracture toughness should be maximised to meet the robustness and reliability constraints outlined in the project brief. The modular payload is also required to meet the aforementioned objectives and is based on a simple design that allows multiple mounting opportunities for a variety of cameras and technology to be implemented to aid bushfire prevention and mitigation. With constraints, objectives and free variables determined depending on each component's loading conditions to ensure system robustness and reliability, material screening and elimination methods are adopted. As seen in the Ashby charts, constraints are applied to the relevant chart to eliminate unsuitable materials. Additionally, objectives like lightweight stiffness can be applied to the chart to determine candidate materials for ranking. Next, the candidate materials are ranked and compared. The method adopted for each component used a utility function and a performance score method. The performance score was established using a rate by average value method, which takes into consideration the relative weighting of each material property and transforms them into a relative score that is used in a utility function to determine the final performance. An example of this method and the outline of calculations is shown in the figure. Properties with qualitative values like manufacturability and corrosion resistance adopt fuzzy numbers to give a quantitative score between 0 and 1 depending on its performance. The highest performing material for each component was carbon fibre reinforced polymer, and to improve the fracture toughness and its operating temperature, a perlite additive epoxy will be also incorporated to ensure system performance and to meet the constraints outlined in the project brief. To verify the material selection and determine which components perform under varied loading conditions, FEA was used. The ANSYS workbench software was employed, and using the ACP pre-post module, each component's overall thickness and layout was determined. To ensure optimum performance, a minimum inverse reserve factor, which uses different composite failure criteria to ensure the component does not fail, 0.7 was established, with 1 meaning failure. Additionally, a maximum of 1 mm total deformation was also used to ensure performance. The results of each component are displayed and show where the maximum deformation inverse reserve factor occur. The maximum equivalent stress was also investigated and used to make design iterations in high stress areas. After material and geometry verification, the final design of the UAVAS was completed. Each animation shows how the mounting and payload attach to their respective drones, and then the assembly of each payload with the mounting structure to give a clear indication of the assembly and final design of each component. The fire suppression payload, as can be seen in the animation, contains an internal pipe structure to direct the Elite A balls to the opening. 3 servo motors are also contained to secure the balls and allow for accurate release of each ball. An internal platform is also designed to be used for added technology required for the operation of the system. Stainless steel fasteners were used throughout for their high service temperature and corrosion resistance. Bonded studs and inserts were also utilised to provide a larger service area and to avoid compressive failures around each joint. To ensure that payloads remain watertight and smoke-proof, high temperature rubber seals are used around each opening, and a rubber grommet is designed for electrical connections between the drone and the payload. To improve image quality and flight performance, a stability system is also utilised, using springs and actuators between the payload and the mounting for ultimate performance. Overall, the UABAS and the design components allow for a holistic system to be completed to aid in bushfire management, both in prevention and mitigation. Each part has been designed to improve the overall impact of the system at an environmental, social and ecological level to ensure optimum performance. Future work of the system includes a full safety analysis, development of a prototype and materials testing of different fibre and epoxy combinations, and a full fireproofing system. Whilst the total cost of the design components is estimated to be $1,700 and a total component mass of 5,250 grams, including the fire suppression balls. I'll now pass on to Callum, who will cover manufacturing, maintenance and fire mitigation. Thank you.
Hello, my name is Callum Kilgariff and I'll be presenting the manufacturing and maintenance segment as well as the fire suppression and hazard reduction function control as part of bushfire mitigation strategy. The activities performed during the life cycle of the advanced materials and technology are aimed at minimising the effects to the Australian ecosystem and society. This portfolio of the projects addresses how the bushfire emergency is assisted by the UABAS in terms of achieving core aims of reliability and effectively removing fireman interference. As an emergency service system, where its function may have lives depending on it, the drone needs to have maximum confidence by ground crews. With core constraints such as reliability in mind, an integrated process for homogeneous production was established to help maintain functionality in trying conditions. Defects are notorious in composites due to their uncertainty in manufacturing and so required optimization. Compression molding was then selected as the final manufacturing method. Several factors make this the most viable option and are addressed by their weighting in the project constraints for manufacturing cost, sustainability, and robustness. The storage logistics of keeping resin, hardener, and fibre separate is much simpler than preventing prepaid materials from degenerating. Intensive power requirements for autoclaving were avoided by implementing curing inside the clamp molds. Precursors can be implemented to optimize material properties, where perlite additives were added to thermally conductive matrices such as phenolic resins. Carbon fibre weave, as discussed in the materials section of the report, is to be hand laid onto the mould, separated to the mould by a layer of gel coat polyester resin with thixotropic additives to provide a good surface finish on the finished product for wear and weather resistance. CME composites were reached out due to their suitability and their RTM department to the project, but were unable to give quotes. A full team of specialists is also recommended to oversee all parts of the system life, from manufacturing, maintenance, and operation. Familiarization with a full-time team will ensure that the system has sufficient oversight to be developed further, expanding its functional capacity. This team would oversee quality assurance at the manufacture in the form of ultrasonic testing of composite parts to ensure that parts are fit for emergency services. Learning curves are eliminated in assembly, maintenance, and operation, where these processes can be adapted to better suit evolving operational needs. The following simulation presents how the early detection from the mother drone will register the ignition of a fire. The system will cross-check images for characteristic color bands to register the presence of flames. Intensity is then measured by the color chrominance. If the size and projected path is deemed suitable for suppression or firebreak generation, the system will send out the necessary assignments for assisting drones. The firebreak function is designed to intersect fire paths going into sensitive locations. Deviation from the path will initiate guidance from the mother drone to the swarm to direct the burn line back into the prescribed area, as shown by the simulation. The suppression drones dropped 0.4 kilogram Elito fire suppression balls onto open flames to suddenly remove the oxygen feed to the fire by covering the area with ammonium phosphate mono, a typical fire extinguishing material. The suppression drones will be primarily targeting spot fires, generated by firebrands that have travelled great distances ahead of the fire front. Such instances are common in the Australian bushfires, as many eucalyptus trees and grass species are easily lifted. Multiple suppression drones can be assigned to provide a blanket drop of more balls if required. Firebreak swarm also need to be deemed safe within their limits. The drones themselves are not suitable for mitigating large fire features such as crowning, but will instead also follow ember storm patterns and mitigate flanking fires. Here, fuel is removed from the fire path, so fast-moving fronts are not able to leap through great expanses of bushland so quickly. This also provides the system with a function outside of bushfire season. The firebreak function can be operated as controlled burning as preemptive hazard removal. As Project Overview mentions, success to this operation will be early detection by the mother drone to correctly direct firefighting energy and resources for both the UABAS and ground services. The following costs were found for assembly parts and mold tools. Surface area and complexity were highlighted by DFMA work and used to approximate mold costs. Fiber volume fraction of 60% was implemented, where 4% of the matrix was perlite additives and the remaining 36% phenyl formaldehyde resin. To conclude, a fire service assisting system was generated to have a meaningful and sustainable impact on the Australian bushfire effort, targeting feasible features such as spotting. Materials and technology were selected following an extreme condition strategy, where functionality wouldn't be interrupted. That concludes the presentation of the UABAV system, final design for the MMAN4020 Thesis B.